Another electrophilic aromatic substitution reaction is a sulfonation reaction, in which you can take concentrated sulfuric acid, and that's it. You can add a sulfol group, which looks like this. Like that. No, I'm missing there. So we add that group, and that is called a sulfol group. Sulfo. We added a sulfol group. Okay. But you may see it not like this. You may see it like this. SO3H. Pay close attention. Sulfuric acid has 4 oxygens. The sulfol group only has 3 oxygens. Right? That's one way to do this. Another way is a different type of reagent, is that you would use sulfur trioxide plus sulfuric acid. And this step, right, or those reagents, is typically called fuming sulfuric acid. So if you just use concentrated sulfuric acid, this reaction would occur, but it'd be really slow. If you want to speed it up, then you do fuming sulfuric acid, which is simply concentrated sulfuric acid mingled with the sulfur trioxide. I'm going to show you that first step of the reaction to generate the electrophile using just this method or this one in pink. But at the end of the day, you're going to get the same electrophile to add that sulfol group to it. Okay? So let's look at the first one, the first part, where we just have sulfuric acid. Okay, when you have sulfuric acid, let's draw 2 of them. Okay, like this. There's one of them. There's the second one. So we have 2 sulfuric acid molecules. What's going to happen is we see that we start with 4 oxygens. We need to only have 3 of the product, so we have to get rid of one. And how can we get rid of an oxygen? We would have to convert it into a good leaving group. And so that would just simply be a proton transfer mechanism, in which now we're going to have this species right here. We have 2 plus the conjugate base, like that. Okay? So now we have those 2 species after the proton transfer mechanism, and then we would do a heterolysis. A heterolysis step. What's that going to look like? Well, this guy's going to fall off, right? And how can we get this water molecule to fall off? Well, we can help force it off. And when we do that, we're going to have double bonded O there, that. Yeah, so that's the bond angles on that's just horrible. Let's fix that. Okay, it would be looking like this. We have that group, just like that, and water has fallen off. Okay. So it's this species right here that a lot of chemists believe is the electrophile of interest. Okay. And so heterolysis, after we do heterolysis, what's going to be the next step? That'd have to be the electrophilic addition step. That's where you're going to take your benzene ring There's our benzene ring. And then the pi electrons are going to come in and attack the sulfur. And then kick that off like that. All right, there's our electrophilic addition step. And so that's going to give us this species right here. S, double bonded O, and then the OH like that. You see now how it only has 3 oxygens? That's positively charged. And now what do we have to have? Is a electrophilic, electrophile elimination. Now, this is the minor difference amongst the previous 4 electrophilic aromatic substitution reactions. So when you go back and compare this reaction to halogenation, nitration, Friedel-Crafts alkylation, and acylation, you will recall that this last step is going to be irreversible. And that would be the electrophile elimination step. But in sulfonation, it's this one that is reversible. Of the 5, that's the only one that's reversible. But what we're going to do now is take one of the bases. Okay, this looks like a really good base, or not a good base, but it's basic in nature. We also have water here. Okay, it doesn't really matter. I like to use water. So that's going to come in all the way over here, grab that proton, put the 2 electrons there to give us our product. SO3H, boom, boom, boom. Now, as you can see, every step in this mechanism is reversible. So yes, we can actually have the sulfol group attached, and then we can take it off if we'd like. And I'll show you that in another video called desulfonation. But before this video concludes, I promised that we would look at this first step right here under fuming sulfuric acid. Okay? So this is the mechanism for just sulfuric acid. Now, let's change it up a bit. Okay, and I shouldn't have erased that. That was actually silly. So we want our sulfuric acid, H₂SO₄, concentrated. Okay, and then we would have to add in our sulfur trioxide. Sulfur trioxide like that. That will also get us to the correct answer. It will just get us to the correct answer faster. All right. So let's see what we could do here. So plus our sulfur trioxide, like that. So we have sulfur trioxide. So what's going to happen mechanistically, we have 2 lone pairs there. We can come and grab the proton from sulfuric acid. And so that would generate our conjugate base. So this species right here would go there. All right. And then that would generate the species that is responsible, that we believe is responsible, that behaves as the electrophile. Plus right there. Okay. So you just remember when in the original, this was the electrophile that's responsible for this reaction? Well, we just generated it without doing a heterolysis step. We just did a simple proton transfer from here to there. Okay. So at the end of the day, we could just say, oh, we didn't need that heterolysis step because we just generated that. And then the mechanism proceeds the same way. All right? So those are the two mechanisms or two ways of looking at it: fuming sulfuric acid or just straight up concentrated sulfuric acid. But maybe I should put this in parentheses saying that this is the fuming. Okay.